Welcome to Abstract Algebra, you crazy mother. Yeah. Okay. This is the course that made me decide to be a math major. Because this is the course that really talks about things that underlay all algebraic and analytic structures that we do. All of the theory of calculus, all of the methods in linear algebra, all of the rationales for why things work the way they do in differential equations come from understanding the structures underneath those procedures. This is the class that talks about them. I was a physical chemistry student before I was a math major. I wanted to build designer pharmaceuticals, and not in a Breaking Bad sort of way. What I wanted to do was map the structure of the activation site. So when a molecule interacts with a cell, it latches on to that cell based on the structures, the bond structure and the physical structure geometry of the chemistry. But mapping a molecule like that, nobody knew how to do. And I said, well, if we can figure out how the structure is going to fold up, what its pattern is, then we can know what it's going to attach to and what the attachment site looks like. So all we have to do is really look at the way things move and fold. We're going to do that in this course. But in order to study that from a physical perspective, I thought you had to study crystallographic structures and X-ray crystallography, and I was doing chemistry because of that. 5 years ago, a gentleman I met, of all places, through the Fountain Pen Club I'm part of, graduate student at the University of Pittsburgh in material science engineering. And he is, with an electron force microscope, mapping the carbon atom chains in a protein activation site. And I pull out notes from 30 years earlier and go, you mean this stuff? And he goes, where the... They didn't know how to do it when I was trying to do it. The tool didn't exist. What he was doing was drawing the physical activation site because they could finally see it, and then figuring out how a molecule would attach on. I got scooped because the tools didn't exist. The theory existed, and that hooked me hard. I don't have to be in the lab to understand how things twist up like that. And then I found out how many more applications it had, and I was hooked. So the study of algebraic structures, rings, integral domains, fields, groups with applications, almost none of those terms will be familiar to you. We've mentioned all of the ideas we're going to use in other places. In Intro to Theory of One Variable Calculus 207, we talked about it a little bit. In calculus, we dropped some hints. In discrete, we started with the basics. The majority of what we do is going to sound completely disconnected from the real world. It isn't, but it sure as hell is going to sound it. But the applications go from physical chemistry to modern cryptography to quantum analysis for quantum computing. They're all here. We're going to get that far into it. We are using John Fraley's and Neil Brand's first course. I like this book a lot better than some of the others we've been asked to use at different points. It leads into a lot of nice places. There is available a Shams outline for group theory. It's about $20. This has a whole bunch of already worked out examples. And since most of this course is based around proving theorem ideas and then working calculations based on those, a lot of good worked out proofs in here that are helpful to read. I'm pretty sure the books are physically at the bookstore as part of the book bundle if you bought in. If not, there are the ISBNs. Go grab them. In a very real sense, this course epitomizes that first objective, to explain the patterns in mathematics. Because this course strips away the labeling ideas and gets at those patterns very substantially. You've seen all of this in every other course. Come to class, please talk to me, engage with the process. Homework is due 2 class periods after we finish the section that covers it. All the due dates are on the assignment tab in Canvas. Each individual section will have a problem list and thus things to turn in. I will grade those specifically. I doubt we will have a tutor. So come see me in office hours as often as you need to. Most of the people who already took this course graduated. So it's an every other year course. I don't have them around to be tutors for you. There are 3 exams, 2 in semester and a final. Where did I put that schedule? Here it is. Exam 1 and what it covers. Exam 2 and its coverage. Exam 3 is comprehensive. It will cover everything. It will emphasize material not previously covered. And I apologize, it's at 8 in the flipping morning. They make the schedule, I just have to live with it. Every single question in this text, every single one of my exam questions so far, I found on the internet at some point. You can skate through this course without ever touching the textbook directly. I don't think it'll help, and the exams might blow your mind. But that brings me to that idea of the AI policy. Because the material is abstract, is theoretical, it may be very time-consuming to chew on. You're going to have to think about these exercises carefully. And that means you may read something and go, what the hell is that? Multiple times. I have fed sections of books into Gemini and said, read this to me like I'm a 9th grader. Read this to me like I'm a 5th grader, because I still don't get it. And it will. So using, and I'm recommending a Gemini as an AI to use because we have it through our Gmail accounts and it is siloed. Seton Hill University data does not go into their general data training pool. They don't get to use us to train their models. So feel free to get it to help you design other problems. Hey, here's the set of exercises. Give me 7 or 8 more. Here's the exam review. Make me 10 more questions. But don't take the AI output and turn it into me like it's your work. Because then I don't know what you know. I know what you can write down. There is the grade distribution. Homework is the single largest portion, but in the long run, it is less than the exams. But that's because, again, this is a course that if you don't spend time in the struggle, you won't gain anything from it. It's one thing to have read something and to be able to regurgitate it. It's another thing to take that and make it you. And that's the quote I had up at the beginning here that I got again from a newsletter. Writing is thinking on paper. Writing is to understanding what digestion is to eating. You just take stuff in, right? Your cheeseburger doesn't end up in your bicep. You break it down, extract things from it, and use that to build you up. Writing does the same thing. As you think about something and write notes or exercises or whatever on it, you extract from the books and the lectures and the other experiences you've had and distill down thoughts that become part of you. Please come to class. It's designed face-to-face and synchronous. I am recording. The recordings will be posted to our Canvas page. There is a YouTube link. As soon as I get the playlist, after I post the first one, that link will go live. You'll be able to get at it. Anything I write will get posted as well. I'm talking about writing as the way to think about this stuff. I'm going to write under this like all my other classes. I'll scan those and upload them as well. Please make sure that your bags are under the table so that if we have to bolt, you can not trip as you get out of here. You'll get Starfish information from this course at least 3 times, I believe. Please check your Seton Hill email or Starfish directly using the launcher in the upper right corner on my sheet. If you need to get to me, send me email. You can always call my office phone and leave a message. The voicemail will get converted to an email and they'll attach the recording right to it, so I'll be able to listen no matter where I am. You saw the schedule, you know when we're doing stuff. Those are the assignments. There may be occasional extra credit problems or things on the exams, but there won't be any. It's December. Here, have a 10-point process. Those don't show up. If I'm harping on something, it's because somebody behind you is looking at me like, what? And I want to make that expression go away. Make sure your email is in Canvas and Griffin Gate appropriately. By default, it's your Seton Hill email, but you can set that to forward to anything. And if you send me an email, I'll respond to it from whatever email address it is. But I won't remember that countrybutterfly25@yahoo.com is you. So I'm going to use your Seton Hill email. If you want it to go somewhere else, please make sure you've got that set up. Phones on silent or vibrate, if possible, please. Say tobacco-free zone. If you're using smokeless tobacco, your cuspidor, if it spills on this floor, we have to sand the whole floor. That's a disaster. Please don't do that. As I said here, I took this course in 1989. It's 37 years ago. And this was mind-blowing. I fell in love here. Stop me, or I will ramble like this no friggin' tomorrow and run you over. If you are stuck on something, stop me. Title IX, I am a mandatory harassment reporter. This does not mean I mandatorily harass you and then report it. It means if you tell me something, I am required to report it. Please don't let that stop you from talking to me. If I observe something, I'm required to report it. If you would rather speak with someone who is not required to report stuff, you may talk to the Blackburn Center, Campus Ministry, the Counseling Center here on campus. They are all exempt from the mandatory reporting guidelines. But if I hear something, I have to go to our Title IX coordinator and tell them, hey, I heard this about these people, you should investigate. If any of you have are legally entitled to accommodations, I am obliged to give them to you. Please work with the Student Services Office on Fifth Admin to get into their system so I can get notification and make that work for us. Once I get their notification, I will have a discussion with you about how to meet all of those obligations in this class to make it work. To be engaged means to talk to me. There will be points where I will go, well, and if it's silent, I don't know what's going on. So please talk back to me. Being in the moment, in the work of this course is weird. If you're an athlete, you're going to go for athletic events, please let me know. I get those forms from the athletic coordinator, Jen Brillmeyer, and that is what I know allows for excused absences and things like that. Academic honesty. I've already explained about getting everything you want on this course online. I don't think that helps. So please make this your work, your class, so you get the most out of it. There's that homework list I was talking about. What questions do you have? If through some unfortunate issue, you're going to be absent, a day homework is due, scan it and email it to me. There's a link to the scanning program I use. You can use the Notes app. You can then airdrop it directly to your MacBook and put it in email. But I'm collecting all of this stuff on paper. I'm grading it on paper. I'm returning it to you. That way, I can see that writing process happening. I hope not to need it, but this camera goes home with me. So if I can't be here, if we get weather issues or whatever, I can do this class remotely. It'll look just like the camera's in front of the desk. You'll be looking down just like you're seeing right now. The problem is I'll be on Zoom. And if this is what the screen is showing, then I can't see you. So how do you ask me things? How do you stop and interrupt? Because if all of us are online at the same time with our mics on, the bandwidth gets jammed up and lags start to happen. And I sound like a badly dubbed Japanese karate movie or something. That's where joining a Discord channel that's already been created for this course on the server that is right there is a good way to get that interaction back. The recordings themselves will be posted to Canvas. The web link usually is in that second link in our section. Once you click that, it'll open a new tab, and then you'll see the list. And I've organized it so it's newest on top. You can rearrange it however you'd like. Talk to me. This is too familiar. We've done this all before. You don't have to worry about it. Okay. Well then, let's hit the ground running. Wrong button. Every subject has its foundational concepts. The things we start from, the things we assume, and really the things we define. A definition is really where we start. And you can't define everything. Some things have to be assumed. They're axiomatic. In geometry, the axiomatic objects are a point, a line, a plane, and we build our definitions from those. But nobody ever says this is what a point is, other than there's our definition, a location in space with no length, no breadth, no width. And then we start talking about points and lines and building from those. In this course, the fundamental object is a set. Now, we did sets in discrete back chapter 2. When you took discrete, A set is a collection of elements. Ideally, they're defined in some unifying fashion, but they could just be a pile of things. There is one unique set that contains no elements. It's called the empty set. It's given that slashed lowercase phi circle with a line through it. Remember our notation from discrete, there exists is that backwards E, the exclamation point, is the uniqueness quantifier. A set can be described by a property and when we're working with this, that's referred to as set builder notation. But we could also explicitly list the set. Whether that set is finite, like this set only has 5 things in it, or infinite, assuming the pattern is clear from the set elements listed. I would make the assumption that this set is designed to be the positive odd integers. Because that's the easiest way to continue this pattern. If it's something else, there better be another way to differentiate it from the odd positive integers, and I don't know what that is at the moment. But sets don't have to be numbers. What makes a set a good object is if you can clearly pick an item of that kind and tell me, is it in the set or not? So let's look at that first set. Jack, give me any number. Is 7 in that first set? Is it in the second set?
Yes.
Is it in the third set? Is it in the fourth set?
No.
So you can look at an object and say, yes, that's in there. No, it isn't. That set is well defined. Now that word clearly there is doing a lot of heavy lifting. Because what is clear to one person may not be to another person. And so it is up to the person to whom it is clear to explain why things are in or not in the given set. You asked about Alice in Wonderland. Well, that's a book. It may or may not be in my office. But if I go to my office and I say, is there a copy of Alice in Wonderland here? And I start looking through all my shelves, and the answer turns out to be no, I know. If the answer, hey, here's my copy of Alice in Wonderland right here, it's in my office, then the answer is yes. A set does not have to be explicitly listed to be well defined like that. But some sets are not well defined regardless. I'm going to define a characteristic of a book. A book refers to itself if somewhere, anywhere in the book, there is a reference to another part of the book. So if we're looking in our textbook, I know in chapter 10, they say, look at figure 8.27 on page 88. They go on to talk about, so we refer back to something somewhere else in the book, right? In Alice in Wonderland, do they ever go, back in chapter 2? I'm going to say no. But there are fiction books that actually do talk about themselves that way. In the Canterbury Tales, later speakers make references to previous speakers' stories. They refer back to themselves. I want you to do me a favor. I want you to go over to the library in Reeves, and I want you to make a list of all the books in Reeves. It's easy. You go up to the library and you go, can I see the entire catalog? And then we should check all the books. And I want you to write down the ones that don't do this. Now, for every book, you can clearly look at this book and say, yes, this book refers to itself, or no, this book does not refer to itself. You agree with that sentence? I've got a list. It's probably not a short list, right? I don't want to have this giant list on a scroll stuck in my computer. I'm going to print it out. I'm going to Control and put it in the book. Here's the question. This is a book in Reeves Library. Does it refer to itself? If it does, then it's in the list of books that don't refer to themselves. Can it? If you just said it referred to itself. No. Which means it's not referring to itself, which means it should be on the list. Hush. This book can't be on the list. It has to be on the list. It can't be on the list. This is a bad set. It's not well defined because I can create an object whose status can't be clearly interpreted as being a member or not. So being a well-defined set prevents me from having crap like this. When we talked about propositions back in the street, we talked about the idea of a statement that was either true or false, not both or neither. Whether this book belongs to the set is both true and false at the same time. That's what I don't want to do. So that would make this a not well-defined set. My goal is to avoid these sorts of paradoxes. I want all of my sets to be well-defined. That should mean that they should be clearly listable with properties or with explicit listings. Make sense? So when we define an object, we're really creating an if and only if condition. Told you this with the street. Ryan, what's a square?
A shape.
Any shape with four sides? Four right angles. That's got four right angles. Is it a square? The sides have to measure equally. So I've just said that a thing is a square when it has four sides, four right angles, and the sides are all the same length. If label square, then these things hold. Now I go look at a shape. It's got four right angles. It's got four sides, and they're all the same length. It must be labeled square. If square, then labeled. If properties, then they're if and only ifs. Aha! Every definition we've ever made is an if and only if statement. And that includes the way we define our sets. Something is in here if it has this property. Well, if it has this property, it must be in my list. So when I have sets, I'll just pick two letters to represent my sets. I can talk about one set being contained in the other. So what does that mean?
Everything in A ultimate B, but
If there's an element that's in A, that also happens to be an element of B. You were going to say but, there's something else, right?
nothing, but it doesn't mean that B has to.
Right. There could be things in B that aren't in A. B could be a larger set or just contain something else. If I want to allow for the possibility that these actually are the same set, I change my notation to act like less than or equal to, right? So subset or possibly equal. We refer to these as strict and non-strict subset behavior. There, I can write it with my notation from discrete. If A is in A, then A is also in B, right? My element A. Now, when I use this version, it is possible to write that sentence. And this is really a trivial proof. If A is an A, then A is an A, isn't it? You said that, so I'm going to believe you. We refer to A as an improper subset of itself. Every set has two subsets. The whole thing, and what else? You make a subset by picking things out of a set, right? So I got this set of stuff and I take some of them and this is my subset. The improper subset takes everything. What is the fewest number of things I could take? I could take 0. What set has nothing in it? The null set, my empty set. And such a set is called trivial. Questions? We actually proved that statement in discrete. Chapter 2, section 2, I think. Maybe through section 1. So you should find that notebook. If I've got sets, I can make new sets from old. The Cartesian product of two or more sets is made by building ordered sequences. If I only have two sets, what I do is I make a new set by taking something from the first set, comma, something from the second set. If I've got more sets, instead of ordered pairs, I'll have ordered triples or ordered quadruples or ordered 17s, depending on how many I've got. You graph because of Cartesian products. When you write a point on the plane, you're really looking at the Cartesian product of the real line and the real line, r cross r, which is why we write that as r squared. When you do Calc 3 and we do three-dimensional geometry, we get x, y, z, it's r by r by r to the third. In linear algebra, you did 7-dimensional matrices, 7 rows, right? Those were elements of R7. That's a Cartesian product. It's just the same set 7 times. But they can be any set. They don't have to be the same set. Frequently, we'll make them different sets. Frequently, we're going to work in sets of numbers. Come back to you. I'm going to use Z for the integers from the German word Zahlen. Some textbooks use a capital J. Q for quotients for the rational numbers. R for the real numbers, C for the complex numbers. That funky looking extra slash in all of these letters denotes them as sets. In most books, they're written in boldface. I don't have boldface pen. Now, the first three of these have an ordering to them. If you think of integers, you have negative integers on the left and positive integers on the right, and they're on a number line. Same thing with rational numbers, same thing with real numbers, they have an order. So we'll think about things like just the positive part. So you might say, I only want to use the positive integers, or I only want to use the positive rationals, or the positive reals. But you can't do that for complex numbers, because complex numbers have two parts to them. Remember, a complex number is something that looks like a plus bi, where I is the square root of -1. So if I have 1 plus 2i, both a and b are positive. But if I have -1 plus 2i, is that a positive number or a negative number? Question doesn't make sense. So we don't think of positive or negative for complex numbers. They're not ordered the same way. In set theory terms, we talk about well-ordering principles. The complex numbers fail to that. But what we can do is we can say, maybe I want to look just at the things that aren't zero, because zero is in every one of those. So if I write Z with a star, or Q with a star, R with a star, or C with a star, that's the non-zero values. And that is frequently useful. Why would I want to make a difference between using positive numbers only, positive and negative, or non-zero only? Because at some point, I'm going to do things with my numbers. When I do things with my numbers, those operations may or may not work when I use all the numbers, or when I use just the positive ones or just the non-zero ones. You can multiply any two numbers, right? Can you divide any two numbers? Why not? But if I'm right, and if I'm in the real numbers, that works. And if I'm in the rational numbers, that works. But in the integers, it doesn't. But even if I'm in the reals, does it work all the time? What's 17 divided by 0? So it might be useful if I'm talking about division that I only want to stay away from 0. Or I might have another operation I want to use where having 0 involved is going to mess with me. So I need to make sure I can say, oh, well, let's not use 0. We'll worry about that one later. Questions? The majority of these preliminary concepts were things we covered in discrete. That's why I'm moving them real quickly here to try and go, you did this, try and remember. Read this section of the textbook closely. If I have two sets A and B, I look at their cross product. I can define a relationship from A to B, where I say A is related to B if the ordered pair A, B is in my set R. So I might define a set A, B. I know. Here is a relationship. I have a list of students at Seton Hill, and I have a list of teams. And A is related to B if student A is on team B. So I can write Jack, football. Yes? I know some of you are on sports teams. I don't remember which ones. So we could write all of those things down. Yes? There are going to be people who don't appear in this relationship, right? Because there are people who are not on teams. It is possible to have one person on multiple teams. And each team is going to have a lot of people on it, right? So I can create this relation between these two sets. We often define relations much more simply. In a set, I think of this as a subset of the Cartesian product of the set with itself. So now I have a relation. Instead of using the letter R, I'm going to use this funky looking symbol made up of two pieces of parallel lines. For never were there two things more equal than two parallel lines. That's where that symbol came from in the 1600s. But if you think about the Cartesian product, I'll have every possible thing in the first set matched with every possible thing in the second set. The only thing that satisfies this is when it's the same element in the first and second spots. Well, that's what equals means. This is the same as that. So even our idea of equality is really a set idea. Questions? When we talked about teams and people, I said one person could be on multiple teams, right? But if I wanted to remove that option, what I create is a function. And that tells me that every initiating student would have one and only one team. Now, a function is a type of relation. So I am still defining F by this Cartesian product idea. But once I have that, I'm going to say, hey, look, there's only one occurrence of A comma something in this subset. We had names for the set A and B. And back in discrete, I called them domain and codomain, but I'm pretty sure all of you went, wait a minute, there was another word I used to use when I talked about functions in algebra. It was domain and range. So what's range if I'm not using B to mean range? Oh, the range of F is the set that we actually hit. For example, the function x squared defined from the real numbers to the real numbers has this lovely property that the codomain is all of R, but the range of F is only the positive stuff. Because you can't square something and get a negative in the real numbers. You can only do that in the complex numbers. Questions? Chapter 2 from discrete. There was one more thing in chapter 2. Cardinality. What was cardinality? Say again?
It's a long summer.
Yeah. It leaked out my brains while I was having a margarita. I understand it. I know we did this. I just have to remember what we did. We were counting. That's how many things are in a set. That's the count of distinct items. Now, if sets are finite, then I can just count them, right? If I want to know how many students are in this course, I just start counting 1, 2, 3, 4. When I run out of people, I'm done. I want to know how many chairs are in the room. I can count, right? It's that when it's finite, that's easy. So if I want to say that two sets are the same size, I can just count them if they're both finite. But when I'm just counting, I've said that just several times, counting is actually not a just process. Counting is a complicated process. Because what you're actually doing when you're counting is you're matching the set of objects to the set of numbers. 1, 2, 3, 4, 5, 6, 7, 8. I'm aligning the chairs in the room with a set of numbers 1 to whatever. And the last number I reach, that's how many things there are. So really what I'm doing is I'm creating a function. And the function goes from my set of numbers to the things that I'm counting. But in order for me to do this right, if we count the chairs in this room correctly, I can't go 1, 2, 3, 4. What am I doing? Counting the same item over and over and over again, right? We have behavior and functions that talk to me about things being different. I need to make sure that the function never counts the same thing twice, right? Which means each thing in S has to be matched up with exactly one different thing in T. And we called it a one-to-one function. Now, it doesn't necessarily matter which chair I count for which number. I just have to count each one differently. I'm going to count the chairs in the room. 1, 2, 3, 4, 5, and done. Why am I wrong? Because I didn't cover them all, right? I have to cover them all. We had a word for that too from discrete. A function was one-to-one if everything was different. It was onto if it covered everything. A function is one-to-one if the outputs were the same, the input had to be the same. A function is onto if everything in the codomain gets hit by something in the domain. So if I think about counting the students in this room, I'm taking the list of numbers from 1 to 4, and I'm putting each of you with a number. And I can't put any of you with the same number, and I can't miss anything. Then I know that they're exactly 40. That's what works for finite sets. But this also works for infinite sets. If I can find a matching function like this, then I can say two infinite sets are the same size. Are you ready for me to blow your minds right out of the room? The following sentence should make all of you say bullshit. The set Z plus means what? Positive integers. The set Z means positive and negative and zero. Clearly, there are more positive, negative, and zero than there are just positive. I got all the positive ones, they got more. They're exactly the same size. At which point most people go, you are lying out your ass. I'm going to show you a one-to-one function. That starts with a positive integer and always gives you any integer. Here's my list of positive integers. Now I'm going to list all the integers, positive and negative. I'm going to start with 0. Do you want to go left or right first? Say again? Left. Left is the negative side. So I'm going to go from 0 to -1. Then I'm going to go to +1. Then I'm going to go to -2. Then I'm going to go to +2. Then I'm going to go to -3. And I'm going to keep bouncing back and forth and back and forth. 0, -1, +1, -2, +2, -3, +2, -4, positive. Am I going to hit all the integers? That's 1-to-1. That's onto. Those two sets are the same damn size. That's annoying as hell. Infinity is weird because it allows things to be infinitely large and contain other infinitely large things and more. I hope it is clear that there are more fractions than there are integers. Nope. I'm just going to use the positive fractions for the moment. If I write this out, I'm writing every possible positive fraction, yes? Now I need to put them in order, the first one, the second one, the third one, the fourth one, right? I'm going to do this by starting in the upper left and going diagonally back and forth, skipping any number I've already come across. Do you want to go from here to the right or down first? So that's second. That's third. That's fourth. I go back up the diagonal. I've already done this. This is 1, right? I've already done that one, so skip it. That's fifth. 6, 7, 8. Am I eventually going to hit them all? So that set's the same size also. This illustration and this idea is on page 5. I would also point out to you that it breaks when I get to the real numbers. All of these sets up here are called countably infinite. And their size is given by the Hebrew letter aleph, from which we get alf in alphabet, aleph sub 0. The real numbers are bigger. The proof is a proof by contradiction done by a guy by the name of George Cantor, and it's called the diagonalization argument. It's in the textbook on page 6. We did it back in discrete, and y'all hated it then, but I know we did it. But these are called cardinal numbers, aleph 0 and the continuum. They measure the size of things. Now, the reason I wanted to bring this up is because we will do a lot of work in finite sets. There is a lot of work in abstract algebra in infinite sets. And some of that work is related to particle physics and chemistry and electromagnetism. There's a lot of really neat that happens there. But that's really complicated, and I don't want to go through it this semester. Not in an introductory level class. Questions? Now I jump all the way to the end of discrete, chapter 9. I want to talk about partitions, because relations gave me the idea in partitions. A partition of a set is a collection of non-empty disjoint subsets that completely exhaust S. What the hell? I want a partition to be a collection of subsets. I want them all to be not empty. I want them to be disjoint. So if they're two different ones, they don't have anything in common. And completely exhausting means that if I put them all together, I get the whole set S. Each and everything in the set S appears in one and only one of those subsets. Those subsets are called cells. You did this. Santino, pick a number. So I'm going to take all the numbers in the integers and I'm going to divide by 6. And I'm going to look at the remainder. What are the possible remainders when you divide by 6? Or, well, let's see. So the remainder would be 0, right? So 0 through 5. Every integer has a remainder when I divide by 6. The remainder is somewhere between 0 and 6. I can think of those as the set of cells. So I could say that is one cell of the partition of the integers. That's another one. All the things whose remainder is 0, all the things whose remainder is 1. And there's no overlap. And if I do 2, 3, 4, and 5, that's a partition. I've written that little bar over to that to say this is the set that contains 0 and all the things that are remainder 0. Now, wait a minute. All of those things have remainder 0, right? They're related to each other. A and B are related if they're in the same cell. This is an equivalence relation. Equivalence relation? What's an equivalence relation? This relation is reflexive. It's symmetric. And it's transitive. And those cells are now called equivalence classes. Guess what? That was the very last thing we did in discrete, chapter 9, section 5. Every relation, every equivalence relation gives me a partition. Every partition gives me an equivalence relation. They're the same thing. Now, here's the stupid ass question. Why? Why am I doing this? I want to use the whole of set definitions and relational ideas to build algebra. Not the algebra of numbers, but the ideas under algebra. And that's where this course is going. I am going to teach you how to do a Rubik's Cube, how to do chemistry, how to do physics, how a PET scan works and a CT scan. Because they all work on these principles. This class is going places. I will see you all on Thursday. Have a wonderful rest of your day.